Unusual applications of quantum computing. Welcome to Module 2, Quantum Weirdness. I'm Dr. Eliza Quantum, and today we're exploring Lecture 13, Unusual Applications of Quantum Computing. Have you ever wondered what happens when the most enigmatic technology of our era, quantum computing, collides with fields we'd never expect? What strange new possibilities emerge when we apply quantum mechanics to solve problems beyond physics and mathematics? Today, we're venturing into the shadows of quantum possibility, where the computational bizarre meets the practically revolutionary. The applications we'll discuss may seem like science fiction, yet they stand at the threshold of becoming our reality. While quantum computing is often discussed in relation to cryptography or materials science, its tendrils are reaching into domains that might surprise you, from the arts to medicine, finance to climate science. Before we dive into these unusual applications, let's briefly revisit what makes quantum computing so fundamentally different from its classical counterpart. Classical computers process information in bits, binary units of 0 or 1. Quantum computers, however, harness the mystifying properties of quantum mechanics through qubits. These qubits exist in superposition, entanglement, and demonstrate quantum interference, allowing them to process information in ways that defy our classical intuition. This isn't just a faster computer. It's an entirely different paradigm of computation that opens doorways to solving problems previously thought unsolvable. Let's begin our journey with biology, a field seemingly distant from quantum physics. One of the most baffling problems in biology is protein folding. Proteins, the molecular machines of life, must fold into specific three-dimensional structures to function properly. Misfolded proteins can lead to diseases like Alzheimer's and Parkinson's. Classical computers struggle with simulating this process due to the astronomical number of possible configurations. Quantum computers, however, can represent multiple protein configurations simultaneously through superposition, potentially solving in minutes what might take classical supercomputers millennia. This capability extends into the perplexing realm of drug discovery. Developing new medications typically takes years and billions of dollars, with most candidates failing during testing. Quantum algorithms can simultaneously evaluate countless molecular interactions between potential drug compounds and biological targets. Pharmaceutical researchers are already exploring quantum computing to identify novel antibiotics against resistant bacteria and antivirals that can adapt to rapidly mutating pathogens. What's particularly enchanting is how quantum computing could help design drugs that were previously unimaginable, because their interactions were too complex to model with classical methods. Perhaps even more thought-provoking is quantum computing's application to genetic analysis. Our DNA contains approximately 3 billion base pairs, creating an intricate code that influences everything from eye color to disease susceptibility. Quantum algorithms could revolutionize how we analyze this genetic labyrinth, identifying subtle patterns in genetic variations across populations or predicting how specific mutations might affect protein function. This could transform personalized medicine, allowing treatments tailored to each person's unique genetic makeup in ways currently unattainable. The COVID-19 pandemic demonstrated our vulnerability to viral threats. Quantum computing offers captivating possibilities for pandemic response. By modeling viral mutations, transmission dynamics, and population movement simultaneously, quantum systems could predict outbreak patterns and evaluate interventions with unprecedented accuracy. Imagine a system that could recommend precise, targeted public health measures based on quantum-powered simulations of how a pathogen might spread through complex social networks. Such capabilities would transform our approach to disease management. Now, let's venture into perhaps the most unexpected territory, the arts. Could a quantum computer create art? The answer is mysteriously affirmative. Quantum random number generators can produce truly random outputs unlike their classical counterparts. Artists and musicians are harnessing this quantum randomness to create pieces that exist at the intersection of determinism and chance. Quantum-generated music utilizes algorithms that translate quantum states into musical notes, creating compositions that are hauntingly unpredictable yet structured. Similarly, visual artists use quantum data to generate images that seem to capture the essence of quantum reality itself, simultaneously ordered and chaotic. The gaming industry, always hungry for innovation, is exploring quantum computing to create procedurally generated worlds with complexity and variation impossible with classical methods. Imagine exploring game environments where quantum algorithms ensure no two players ever experience exactly the same world, yet each world remains internally consistent and compelling. Or consider AI characters whose behaviors emerge from quantum processes, making them eerily unpredictable and lifelike. In film and special effects, quantum computing's ability to solve complex physics simulations could revolutionize how we create visual spectacles. Realistic fluid dynamics, cloth simulations, and lighting effects that currently require massive render farms might be calculated in real time. Directors could visualize impossible scenes with perfect physical accuracy, blurring the line between the imaginable and the filmable. The uncanny valley, that sense something digital isn't quite real, might finally be crossed through quantum-precise simulations. Perhaps most baffling is the application of quantum computing to creative writing. Researchers are developing quantum language models that can exist in superpositions of narrative possibilities, potentially generating stories with plot structures and character developments that classical algorithms could never conceive. These quantum storytellers might someday produce literature that captures the contradictory nature of human experience in ways that feel profoundly authentic, because they emerge from systems that, like human consciousness, aren't bound by binary logic. Moving to finance, high-frequency trading firms are investigating quantum computing's potential to analyze market patterns and execute trades at speeds that would render current algorithmic trading primitive by comparison. The ability to simultaneously evaluate multiple market scenarios could give quantum-powered trading systems an edge measured in nanoseconds, an eternity in markets where billions change hands in milliseconds. Risk assessment, the cornerstone of insurance and financial services, might be transformed by quantum computing's facility with uncertainty. Quantum algorithms could model complex, interconnected risks more accurately than classical methods. Insurance companies could price policies more precisely, while banks could evaluate loan applications with more nuanced risk profiles, potentially expanding financial access to traditionally underserved populations through more accurate risk evaluation. The cryptocurrency world watches quantum development with both excitement and trepidation. While quantum computers could revolutionize blockchain validation, they also threaten to break the cryptographic foundations of many digital currencies. This has sparked a race to develop quantum-resistant cryptocurrencies, a fascinating example of how an emerging technology forces innovation in an adjacent field. Economic modeling, traditionally limited by computational constraints, could enter a new era of complexity with quantum computing. Economists might finally be able to model entire economies with individual-level detail, capturing emergent phenomena that current macro models miss. Such models could help design more effective policies for everything from reducing wealth inequality to managing inflation, by revealing subtle causal relationships invisible to classical analysis. Addressing climate change requires understanding extraordinarily complex systems. Quantum computing offers hope for more accurate climate models that incorporate feedback loops and chaotic elements that defeat classical simulations. These enhanced models could pinpoint the most effective interventions for mitigating climate impacts, potentially saving trillions in misdirected efforts. Renewable energy faces distribution challenges. How to optimize power delivery across vast, interconnected grids with variable production and consumption. Quantum optimization algorithms could manage these networks with unprecedented efficiency, reducing waste and maximizing clean energy utilization. Such systems might navigate the mind-boggling complexity of balancing thousands of energy sources and millions of consumers in real time, something beyond classical computing's reach. Material discovery for environmental applications represents another frontier. Quantum computers could simulate novel materials for carbon capture, water purification, and energy storage at the atomic level. This could accelerate the discovery of materials with properties that seem almost magical, like membranes that capture CO2 while letting other gases pass, or supercapacitors that charge in seconds and power vehicles for hours. Ecological systems, with their countless interdependencies, challenge our predictive abilities. Quantum algorithms might model these systems with sufficient fidelity to anticipate cascading effects from changes like species loss or habitat fragmentation. Conservation biologists could use these models to design interventions that preserve biodiversity with minimal disruption, potentially averting ecological collapses before they begin. As we've seen, quantum computing's unusual applications transcend traditional disciplinary boundaries. Biology intertwines with physics, art merges with mathematics, and finance blends with quantum mechanics. This cross-pollination of fields represents a fundamental shift in how we approach problem-solving, suggesting a future where our categorizations of knowledge become increasingly fluid. However, these possibilities raise profound ethical questions. Will quantum-enabled drug discovery be equitably available? Who controls quantum financial algorithms that could destabilize markets? How do we ensure quantum creative systems don't homogenize cultural expression? These questions demand thoughtful consideration as the technology advances. As we conclude our exploration of quantum computing's unusual applications, I leave you with this thought. What thoroughly impossible problem in your field might quantum computing eventually solve? And how might that solution transform our understanding of not just the problem, but reality itself? The most captivating aspect of quantum computing may not be the answers it provides, but the questions it allows us to ask for the first time. Thank you for joining me on this journey through the Quantum Bazaar.